Almost every program can have errors, and the method the programming language provides for working with them matters a lot. There's a few different ways to do it, and I'll cover a lot of them today. First up, we'll cover exceptions. They're a popular system in a lot of languages, but they've fallen out of favor for a lot of people, and let's get into why. Exceptions are a mechanism of propagating errors. When some code has a problem, it throws an exception, which then gets caught somewhere up in the stack. The nice thing about exceptions is that it's very easy to prevent invalid states. If code has a problem, it exits immediately, regardless of the rest of the control flow of the function. This is absolutely the sort of behavior that you do want for some errors, but not most of them. That's why they're called exceptions. They're good for exceptional circumstances, times when a total program shutdown is the reasonable default. If your computer is out of memory, most programs don't have a way to deal with that, so it makes sense to crash. Same thing with a failed assertion. But the lines get a bit blurry with some errors. What about a missing file? Well, some programs, particularly command line ones, are fine to crash on that, but even still, they should probably print an error. And any real software shouldn't crash on a missing file. You should get an error pop-up, and the program should continue like normal. Some languages get a little absurd with exceptions, like Python. Python uses exceptions everywhere, even for things like iterators. If you've ever looked into how Python iterators work, you might know that a for loop will only end when the iterator throws a stop iteration error, which is honestly just a little bit weird. This behavior has changed a bit in newer versions, but from what I can see, exceptions are still used. Exceptions can generally be split into two categories, checked and unchecked. A lot of languages, particularly ones with dynamic typing, will only support unchecked exceptions. That is, exceptions whose control flow is implicit. Checked exceptions, on the other hand, are required to be explicitly listed in the function signature. In a language like Java, most exceptions are checked, but some system-level exceptions are unchecked. Things like an I/O error are checked exceptions, but out-of-bounds indexing and memory errors are unchecked. Personally, I'd rate exceptions a solid 6 out of 10. When propagation is the behavior you want, they're a pretty solid approach, but when it's the only mechanism inside a language, you wind up writing a lot of verbose try-catch code that gets in the way of your real logic, and the scoping that these blocks create force a large amount of code to be moved into that try block. Otherwise, you end up accidentally back at the same problem of invalid states. The biggest problem with exceptions is that they're really designed to be used in an object-oriented way. You need some level of hierarchy with exceptions, that way you can catch multiple different types at once. Obviously, there are a ton of other ways to add relation to your types, but inheritance is the primary way to get these implicit hierarchies. Next, I'll talk about sum types for errors, something like Rust or Gleam's result types or Haskell's either. The idea here is that we return one thing that's either a value or an error, including a small tag to determine which is which. This approach is amazing, but only in certain programming paradigms. To work with this style of errors, a language really needs sum types that are automatically tagged, as well as good pattern matching. A lot of languages just don't have these features because it doesn't work well with the design of the language. One example is C++, which tried shoving this stuff into a standard library without language-level support and wound up creating a mess. In Rust, you do get error propagation via the question mark operator, which gives you explicit behavior similar to the automatic propagation of exceptions. The benefit of this behavior is that all of the errors look like checked exceptions, making it always very clear what errors happen where. One downside of this operator is that it's directly tying language syntax to the standard library, since question mark only works on the built-in types result and option. However, there is an experimental Rust feature that allows this operator to be overloaded for custom types, as well as a new language feature for scoping the propagation, which clears up the main issues with the feature. Overall, I'd give sum type-based error handling a solid 8 out of 10. It's flexible enough to make it work for all sorts of different error types, so you can use it for any error data you want. The only real downside is that you can't do it in every language. It really requires a total language focused on that style of programming. Now I'll get into what Zig and C3 do. I don't exactly know what to call it, but it's basically a compromise between procedural programming and sum types. By integrating the error types as a direct language feature, you can skirt past the need for things like pattern matching. The downside here is that errors become special values of a special type, so you lose the ability to store arbitrary information inside them. C3 and Zig both come with a handful of syntax for working with these error types, allowing you to define variables that may be errors, run code when an error was returned, or propagate values. C3 takes this a bit further, allowing you to do operations on optional values, where the error will just pass through if it exists. The real downside to C3's approach is that there's no way to specify what errors a function may return, only that it might return an error. This means that it's really difficult to guarantee that you've handled all of the possible error cases. Sentinel values are a super common one, which you'll see in almost every language. Alongside whatever mechanism the language actually uses, some functions will just return a special value to indicate that they failed, like -1 or null. It honestly sucks though, and I'm not sure why we do it. If you're in a language that only uses exceptions, having a sentinel value may seem like a great alternative, but when you're used to having errors as values, it feels pretty bad. The only time when sentinel values actually make sense are when they're returning a default value, especially one that actually makes sense in the context. But that usually doesn't happen. Most sentinel values are either -1 or null, so you have to do an explicit check. Errors as values is sort of a trendy term these days, but I feel like very few languages fully do it. To me, errors as values is a step further than some types. It means doing something like what Go does. I've also seen Typescript developers take this up a little bit, as well as C++. In Go, functions simply return an error alongside their value. There are a bunch of different ways to make errors, but because the built-in error type is an interface, you can attach pretty much any data you want. Sometimes, in C++ and in Typescript, you'll see functions that return tuples to represent the error, which has the same idea. The main downside to this type of error handling is that if the language doesn't provide tools for it, you're left with manually checking it, which gets a bit verbose. That's why it's time for the final language I'm talking about in this video, Odin. Odin's errors are a bit of a mix between Zig and Go, which is actually true of a lot of the language. It has keywords for propagating errors, providing default values, and a few other control flow features, but the key difference is that these keywords don't expect any built-in type. Instead, you can use the keywords on a bunch of different types. If your errors are basic and don't require any special data, you can just use a regular enum. This gives you the same behavior as in Zig, but without requiring any special types. If you do want to attach data to an error, it's trivial to do so, because unions can also be used with the error handling keywords. I won't get into the exact behavior of Odin unions in this video, but they can be used to represent an optional type. So something like this allows you to return any data you want in your error. Personally, Odin's system is my favorite. It integrates nicely with the procedural style and doesn't overwhelm the language. It seamlessly works with the style of errors that people are used to, while still giving you explicit control over the behavior without being too verbose. It also avoids all of the allocations that are required when going through interfaces, but if you do like that behavior, then you could always make it work if you wanted. It's just a bit of a pain to set up, which makes sense because it's kind of a weird approach. There are a few types of error that I didn't mention, like Erlang's let it crash philosophy, but that's still exceptions under the hood. The only difference is that Erlang's exceptions stop at process boundaries, so a common pattern is to use short-lived processes themselves as your equivalent to a try-catch block, so that if an operation fails, you just let that process crash and handle it appropriately from the parent. Another thing I didn't really mention was error codes, like you would get from SDL or from OpenGL. I don't know any languages that use error codes as their primary way of handling errors, so I would generally bunch them in with Sentinel values. Anyways, that's it for this video. If you watched this far, you might want to subscribe, and check out other videos on my channel. Feel free to leave a comment with any questions or suggestions, and hopefully, I'll see you next week.